There.
All right. All right. Yeah, sounds good. Yeah. Yeah, I guess I can only see my screen here. So if there are questions, I guess during, you can certainly, just stop me throughout. But otherwise, yeah, I'll look forward to reading those at the end. And all right. Well, first off, I'd like to say thank you everybody for, giving me this opportunity to talk about some of my research here. I'm Andrew Dzambo. I am a research scientist at the CRO Cooperative Institute for Severe and High Impact Weather and Research Operations at the University of Oklahoma. Greg McFarquhar, he is my advisor, supervisor, whatever you'd like to call him. He's been a great, fantastic mentor for the last 2.5 years. Started with a postdoc as him in 2020. I'm currently moved up to research scientist a couple months ago. So this is most of my postdoc and some of my current and ongoing work with the I guess the gig I have going with Greg at this moment here. So excuse me. So we'll get started here. So I'll try to, in my, actually, okay, I have to click here. All right, so we'll, just kind of get started here, just, to kind of build up a little bit what's the basis of the problem and like, what are we thinking about in terms of the context? Like, why are we, caring about, constraining uncertainties in ice particle fall velocities, especially with airborne measurements, from these field campaigns that we discussed where, you can't really get like a true measurement of fall velocity. So that's kind of the thing that I want to keep people in mind. So to get started, one of the most well-known challenges facing weather and climate communities, of course, involves accurately representing clouds and cloud processes. That's, for everybody here, we all work on some aspect of that problem. And despite their ubiquity, I remind myself this all the time just to, stay grounded in the problem, but there's many limitations that exist with them, despite, the fact that they exist all around us. We can look outside our window, we see them, but there's so much uncertainty that still needs to be resolved with them. The three big measurement platforms that we have for cloud observations, of course, are radar, airborne in situ, airborne remote sensing, of course, too, laboratory. You could also add, satellites on here as well for certain. Probably should have added that on here, but just as a example, like, radars, we get 2D and 3D structures pretty easily. We'll show you how we use a little bit of 2D and 3D WSR88D data in the talk here, like for this particular work here. But one of the limitations, of course, is that you need multiple frequencies to resolve both clouds and precipitation. Airborne in situ, of course, is the best way to target individual cloud properties in variable environments, but the thing with airborne campaigns, of course, is that they are very, very expensive. They take many years of planning and are limited ultimately, in just how many observations you ultimately get. Because even when you do get the aircraft, as I've learned, through Greg and, just my own reading here, you can have, 10 to 15 flights for a field campaign, and there will be at least a couple where, at least one of the cloud probe instruments has, it's either gone down, it didn't work properly. So it's really takes many years and a lot of a good effort to build a good database of in situ measurements. But in the context of fall velocity, laboratory measurements are, definitely like, by far the best that we have here. They're limited to the ground, for obvious reasons. But you can study cloud particle growth through its entire life cycle. You can image them, you can actually watch and get a true measurement. So going back to studies like Locatelli and Hobbs, in some of the original, I forget, I think it's Nakata back in the 1930s and then 1950s and 60s, where they were taking measurements off of Mount Fuji in Japan. Those are some of the seminal measurements for ice particle fall velocity, that, we still use in many applications here. So of course, when we take these measurements, they ultimately become parameterization schemes, because in order to, get cloud scale processes, that would take a lot of computing power, a lot of time, and a lot of resources. It's very computationally expensive on a large scale model. So of course, the best way, given our current limitations now, is to be able to take what we have existing, and make it work as best as possible, such that, the parameterization would work just as well as if, we could fully resolve it in a large scale global climate model. A lot of these biases, of course, are pretty well documented in the literature, when looking at global modeling studies of, clouds, especially in like under measured parts of the world, like the Southern Ocean, the Southeast Atlantic, and even the Arctic to a degree. It's just really hard to get measurements up there and then take those measurements and build and tune parameterization schemes. So this is a good segue then to my bottom point here, I guess, where we talk about cloud particle size distribution. So, they're probably the best, most tried and true way, that gives us something that's very accurate, obviously still needs improved, of course, but, we represent, properties like mass, velocity, particle size distribution as, some sort of exponential or gamma function. So, mass dimension relationship, velocity dimension relationship, they take, parameters like A and B or alpha and beta. And, given that that's what the model ultimately uses, it makes logical sense, I guess, to, look at those. What do these coefficients mean physically? And, find what sets of measurements, produce those coefficients. Like, in Locatelli and Hubs, for example, they, quantified, I think, 16 or 17 different particle habits, like different sorts of grapple, dendrites, columns, bullets. They did that by isolating, the certain, ice particles. They measured, like how fast it fell, and then, they fit, parameter to the maximum dimension that they could see, and then come up with the measurement that way. So if there's more ways to observe that, then of course, the more measurements that you have, the more possible constraints that you have to the individual alpha and beta for fall velocity, or A and B for mass dimension, or if you're looking at particle size distribution, your n naught, your gamma, and your slope parameters. So this led Greg McFarquhar et al. 2015. So, the basis for everything that you will see for the remainder of this talk here comes from his 2015 paper, where he quantified three-dimensional surfaces of equally realizable n naught, mu, and gamma for particle size distributions from the ISTAC campaign. So going through, a process where what amounted to, gamma, or not a gamma best fit, but a chi-square minimization procedure, where, he took all of his particle size distributions, and given uncertainties in certain measurements, he could find, certain flexibility, I guess, in all of the parameters where, given the uncertainties, you could fit any combination of n naught, mu, and gamma, and that would give you a reasonable particle size distribution that fell somewhere within that surface here. So, it obviously looks arbitrary here. It's tough to really wrap your head around without seeing like what cloud you were actually measuring, or the database of clouds that ultimately were measured here. But the concept really here is that, you come up with an ellipsoid if you're looking at, 3 parameters, or you look at surfaces if you're looking at 2 different parameters here. So that's kind of the basic concept here. So his, like, the framework for all of, future studies that have come from this have been on this, one, method and study that Greg had did here. Greg had many co-authors and a lot of help on this, of course, and should acknowledge that as well. So, but the idea there was, kind of set there. And of course, the flexibility of being able to tune any sort of combination of parameters to, look at uncertainties in the, particle size distributions was intended, of course, to, be expanded upon. So, not just for size distributions, but mass dimension, area dimension, velocity dimension. So the next study, I guess, that came about this, 4 years later, his, PhD student, Joe Finland, he quantified equally plausible A and B and mass dimension relationships from the MC3 campaign. So, building off of that, Joe had used, in his work here, he used onboard Nevzorov probe measurements, and he used ground-based WSR 88D, like co-located reflectivity measurements. So one might think, of course, well documented in the literature that the Nevzorov probe has, it has issues with shattering. There's been shattering corrections done with that, and then, apparently, when we get reviews back on the Nevzorov probe, it's pretty common to say, like, yeah, it's there's these pretty well-known issues. Why use it as a mass measurement? Well, that it goes the framework is designed, to kind of work with any instrument and any sort of limitation, provided it's physically reasonable for the quantity you're going after, like velocity or mass, for example. So in this particular case, Joe was able to say, well, we understand that the shattering produces this sort of uncertainty in the mass relationships, and we know that reflectivity, measured by the WSR88D, as a secondary like mass estimate, from a secondary source, it'll have an uncertainty on the order of 1, maybe 2 dB or so. So you can quantify that, and like obviously the more uncertainty that's in your truth case, whatever you choose that to be, the more uncertainty, the bigger the surface you're going to have, because it implies, well, given these sets of uncertainties, it follows that you'll have more ranges of A and more ranges of B in a mass dimension relationship that you can use. So that's kind of what goes into each of these surfaces that you see here. I won't have nearly enough time, I guess, to just talk about all of the surfaces here, of course, but the main point being here is that the more uncertainty that you have in your underlying truth estimates, the bigger the surface that you'll have here. Really want to hammer that home. How the surfaces are shaped, are definitely more function of the environment, what you're flying through, and what we really want to focus on, I think, is just airborne ice phase measurements only. So, assume that to be the case here. All right, so just now focusing a little more specifically on ice particle fall velocity, it's of course extremely important for a wide variety of atmospheric science applications. Why I went after this problem is, like I did, much of my background is in like meteorology and like just general like climate energetics. So I think about these problems in terms of like water vapor redistribution. If a set amount of water vapor is at one altitude in the atmosphere and it precipitates one to, say like 500 meters or several kilometers below where it should be, that's obviously going to change, the radiative balance in the atmosphere. And therefore that's going to propagate forward in time as an error of sorts. So getting the fall velocity question right, in my worldview, of course, is extremely important, even if it's on a relatively small scale. Others would argue that, getting fall velocity to within a couple 100% is, that's, you're doing great, but why care about, smaller scale stuff, especially ice? I argue it's very important. But to kind of fix or bridge this observation gap here, we need to really focus on measurements from the aircraft here. And even though we don't have true airborne measurements just yet, we can certainly derive a best estimate data set of in situ particle fall velocities, where you can look at, you can derive it from particle mass, shape, and size distribution data, of course. So to kind of get at our main goals, of course, we want to continue building this framework in a way that allows for direct comparison between observation estimated fall velocity and bulk microphysics modeled fall velocity. So there's much work to really get to that second point where we're really ready to, run it in war for another weather model here. But that's, just kind of the underlying goal. Like that's the overarching, like the 5 to 10 year goal that we see with, this work that is ongoing here. So first science question. So we're thinking about, fall velocities, why it's important. What is the general premise of the framework? Just making it as simple as possible for this talk here. After developing the framework to evaluate uncertainty sources in ice particle fall velocity, do relative uncertainties change for varying environmental regimes? So of course, the talk here today, of course, is on MC3. MC3 was the mid-latitude continental cloud and continental convection cloud experiment. So basically measuring supercell thunderstorms and QLCS type convection, across the, Midwest United States. And then the impacts, of course, is focusing on snowstorms over the East Coast. So, we're slowly building, the number of like the types of environmental conditions that we can use the same cloud probe measurements here for. So again, just went over MC3 here. So of course, we're all cloud physicists here. So what measurements are we using here? What we're doing here is, like for MC3, we use the 2DC and HVPS. use everything between 150 microns to 1 millimeter, and then we use HVPS measurements above 1 millimeter to get a full look at the size distribution, and then we derive, of course, our mass dimension and velocity dimension and terminal velocities, of course, from where we get everything else here. All of this is processed using, updated the UIOps, University of Illinois, Oklahoma optical array probe software package. I wanted to point out too, this is quite important for fall velocities, especially, is noting what are the habit classifications. We use a current version of the Holroyd 1987 classification here, which, using probe data, you can look at, it'll automatically classify based on a method that we see here. So in this particular study, so recently published work that's Greg, myself, and Joe, just put out, we looked at two cases here. These, thought this would show up a little bigger on the screen here, but for the MC3E database or cases, we looked at primarily May 20th and May 23rd, 2011. The first case was a stratiform, stratiform ice event where, the aircraft, I believe, measured trailing, stratiform, of course, at about, anywhere between -10 to -30 or so Celsius. And then the second case on May 23rd was a very, very good anvil cirrus case, that was, with a lot of good data and whatnot from that. So of course, a general question to ask was, what do size distributions look like for the individual habits produced by the software here? So we have this in mind here. So I want to show two things here. So first is generally that many of the particles, they tend to fall on the, they're on the, for the May 20th case, they ended up being mostly hexagonal, and for the, for the May 23rd case, we ended up with a lot of dendrites. But in both cases, we actually ended up with a significant fraction of tiny particles. So meaning that it was just, there was definitely a particle there, but it was too small relative to the diode sizes to fully accurately resolve what exact shape it was. So and I think you see this pretty well here in the fact that, at around 1 millimeter, so the cutoff that we use between the 2DC and the HVPS measurement here, there's definitely a little bit of a discontinuity that forms here. This is ultimately became a motivation for continuing, how well, what are we ultimately missing when we, look at data that's around that 1 millimeter or so demarcation point here. The good thing for this study here, I don't know if I put this in the slides here, but we did find that 95% of the mass in both of these flights that we analyzed ended up coming from ice particles much less than 1 millimeter. So mostly between the 200 to 700 micron size range. So the fact that we're really not getting that much more data by, going through the effort of addressing this discontinuity in the habit measurements is kind of important, but good to make a plot like this just to make sure okay, there's data not accidentally falling through the cracks and to make sure that it's fully addressed. So now that we have our habit information kind of in the back of our minds here, we want to look at next, of course, is the, how we're actually making sure we get a reasonable weighted computation here. So for these plots here, I show a couple of different things here. So the first, of course, is just these are mass weighted 10-second average fall velocity across the two flights here that we chose here. So May 20th on the left, May 23rd on the right. And I put two different measurements here, or two different estimates here. One is using the Mitchell 1996 method, and then I'm using and then in the blue is the Heimsfield and Westbrook method, which is effectively the same as the Mitchell 1996 method, but only it adds a correction factor in the area ratio, to give a more accurate, fall velocity estimate, or weighted fall velocity estimate, excuse me. So, thinking about just even that little bit of a difference there, the difference between, the Heimsfield Westbrook method and the Mitchell method, somewhere on the order, depending on the, total amount of ice that you have there and, the variability, you end up with, 0.05 to 0.115 and for either of these flights here. So how significant that is, it was a question I had when I started doing this, but when we think of this in terms of a percent difference, like in the May 20th cases, this amounts to about a 10 to 15% cases. The gray shading I should point out here is the flight legs that we used individually here. So, focus only on where there's gray shading here. Those are the flight legs that we ended up selecting here. It came out pretty cleanly anyways, but yeah, so 4 flights in May 20th and 5 flights in May 23rd here. Yeah, for May 23rd, like just the difference between the two methods here ultimately amounts to about a 25 to 30% difference here. So just from these two different methods. So one of the big questions I had then as well, if you can, depending on the assumption that you use, how much uncertainty do you get just from area ratio? Easy thing to test, I think, using this framework here. So this goes to then the kind of the crux of the ultimate method here that we're trying to use here. So we adapted more or less 3 versions of the methodology. So there's Greg's method in 2015, Joe's in 2019, and then he did this for dimension relation, or just maximum dimension, in his 2020 atmosphere paper. And we more or less do the same here to minimize chi-square for fall velocity. So it's basically the difference between what we take to be an observed, or in this case, a best estimate, because it's not truly an observed fall velocity. And we take that difference from that as estimated by a size distribution that you would compute using a velocity dimension relationship. So you can think of, in this V difference equation here, the left side like VM or Z, so meaning mass weighted or reflectivity weighted, minus the mass or reflectivity weighted derived from the size distribution that you assign an alpha and a beta to. So whatever difference you get there, you could naturally see that, the smallest difference, of course, is going to come from the best fitting or minimized alpha and beta. So that's kind of the thing here. All data in this talk here, of course, are averaged by every 10 seconds here. Now, you can get your minimized chi-square that way. Then the second thing is you need to assign how much flexibility, or what's the surface, or, there's many ways you can put this, I guess, here, but following the, chi-square V equation here for fall velocity, your minimized fall velocity, that gives you the best estimate of your data set here. The delta chi V squared is your uncertainty or your variability. And given that, okay, sorry. So the size of that will be your maximum of the natural variability, which is assigned chi-squared min. So meaning that if you just fly through and there's atmospheric turbulence or gravity waves or some other phenomenon going on, you're going to get some sort of variability in your cloud measurements just based on the fact that nature exists, to put it simply. And then depending on the quality of your measurements, that can affect any remaining term that you want here. You can put as many as you want here. So for our study, we ended up testing 3. We tested area ratio and chi-square 1, maximum dimension and chi-square 2, a number concentration and chi-square 3. If you have more measurements and you have other uncertainties that you want to address, you can add a chi-square 4, chi-square 5. You can add 15 of these if you'd like. And then finding the maximum one, that contributes the most uncertainty, that's the one that we assign to being equally plausible, because it naturally follows that, if one uncertainty source is much, much less than the other, then, you can effectively ignore it because another source of uncertainty is contributing that much more to it. So this is a good way to quantify error in a relative sense, and it gives us a really great way to look at how important measurement uncertainties are relative to Mother Nature itself. That's the way I like to think about this here. So I'll try to move this just a little bit quicker here. For the study here, we have to compute both mass and reflectivity weighted fall velocities. We show all results here as surfaces of alpha and beta coefficients. We put the Locatelli and Hobbs results on here just so there's a reference for everybody here. So we, assign the, little black and red dots depending on the plot here. Those will be for velocity dimension. And then, the observations that we use to constrain for this here are ice water content from airborne Navzara probe measurements in MC3, and then of course ground-based radar reflectivity from the Vance Air Force Base. So first question here, first set of results that I'm about to show here. How does equally plausible mass dimension relationship affect equally plausible VD? And the subcontext for this is, does mass weighting or reflectivity weighting ultimately matter? So we've noted, through the discussion with the Nevzarov probe, what if we don't have a mass measurement and we only have reflectivity data? There's a way to test that too. So I'm going to show results for both reflectivity only data and full mass weighting, where you have a mass constraint and you also have further constraint by the reflectivity. I should also point out here, like, if I didn't make this apparent at the beginning, but one thing with reflectivity weighting is that it'll allow mass weighting in such a way that where if the aircraft is flying through a region of cloud where the reflectivity might be, it's not necessarily going to be caught by the mass weighting. So it has a way of capturing like the highest or the largest ice particles that could be shattered by the Nevzarov probe. So that's the purpose of including the reflectivity measurements in this. I'll just continue. Okay, I will, restart here. Okay, so the question here is, if we know mass dimension, if we use the framework for equally plausible mass dimension relationships and we just change that, what does the equally plausible velocity dimension relationships come out just from that alone? So totally discounting measurement uncertainties, from any airborne well, of course they would affect the, mass dimension relationships, but this is sort of the result that you would get. So, as you go from alpha values of, 1 to 2, all the way up to 5 and 10 or so, you get these large surfaces here where, in this mass weighting scheme here, you get a decent amount of uncertainty, it looks like here. So you go, the betas, of course, change given, that you're flying in, much warmer temperatures up here. And then as you go colder, beta tends to come down just a little bit here. But what I want to draw everybody's attention to here is, just watch the coloring here. So this is the percent occurrence of like the equally plausible mass dimension relationships that would produce an equally plausible velocity dimension relationship, okay? If you use reflectivity weighting, you end up with many, many less uncertainty sources, or excuse me, not uncertainty sources, equally plausible mass dimension relationships that could solve that particular alpha or beta for the velocity dimension here. So there's definitely a difference in choosing mass or reflectivity. In a relative sense, like if you're comparing uncertainty to natural variability, it won't matter too much because everything will scale according to, how you choose mass or reflectivity weighting. But in this general sense, it will make a difference as to where your uncertainty framework is shifted. Now, for the May 23rd case, we definitely see the same thing here. So for mass weighting, you see it's much better constrained when you actually have a mass measurement. Like you're much more confident, that the error uncertainty is that like it's anywhere between 90 to 100% of the points everywhere that you look at for all 5 of the flight legs that we chose here. Reflectivity weighting, you get a wider range. The betas tend to shift a little bit upward, due to how it's handling, the largest sizes, and ultimately reflectivity becomes much less sensitive to smaller ice particle size distributions, of course, too. So there's that. I wanted, to point that out there because, again, there's many, many ways you can apply this framework here. This is just one of them. What if you take your uncertainty sources to be just all of those from equally plausible mass dimension relationships? Now, how does natural variability of ice particle velocity compared to uncertainty and area ratio size distribution maximum dimension? This is the bread and butter here. This is kind of the the big thing that we tested and we were able to succeed in doing here for fall velocity measurements here. So this is our first flight leg here. So we have 4 different legs here, same as the ones that we just showed here, for, about -6, -10, -23, and -16 again. Temperature regimes, equal altitude, approximately equal temperature, to within, several tenths of a Kelvin or so. So when we do mass weighting, we end up with the blue shaded surfaces here, and then the reflectivity weighted are the overlaid dashed surfaces here. And then the minimized alpha and beta for that particular flight leg, depending on the weighting scheme, are denoted as a black square, which you could see at about alpha of, 7.5 and a beta of about 0.6 here for, in this top left plot here. And then for mass weighted, it's much more in line with the Locatelli-Hobbs, their derivations here, at about, 0.1 and, 0.24 for a beta or so. So that was definitely encouraging. We saw this for all 9 of our flights here, May 20th and May 23rd here. I'm just going to flip back and forth here to talk about it because I really like the results themselves. Like, I want you to think about them more generally and how this can be applied rather than this is the answer for, mid-latitude convective clouds, because, at the end of the day, we only had, 2 good flights where we had all of the data that we could possibly want here to look at. So it's really meant to be like a starter, like a proof of concept and a proof of how we can continue using this and thinking about these results physically for giving good estimates of uncertainty and being able to translate uncertainties that you get from Mother Nature and measurements to, models where, that's where they ultimately need tested, and you need your alpha and beta constraint for better measurements there. But I will say, so moving on to the May 23rd case here, what we found really interesting here was, that the surfaces overlaid for the reflectivity and the mass weighting scheme varied quite considerably here. We'll say, we continue to see this behavior where the reflectivity weighting, continue to produce larger betas for, the same alpha ranges. The alpha is going out to 25, of course, like, this is meant to show just like how big the surfaces can go, not that they, they're very common in the literature. In fact, most alpha and beta that are derived, are much less than like 1 or 2 alpha or so. So this is quite extreme here. But again, this is just to show, it can be possible in certain cases, like especially for highly dense ice particles here. But so yeah, that, just in general, we saw more uncertainty from natural variability. That's ultimately what came about all of these results here. The blue surfaces are large, as were the reflectivity weighted here, just in terms of the amount that they took here. So you can see, a lot of, you could get the surfaces there, that's kind of the big thing here. Now, I apologize for throwing a bunch of numbers in a single table, like I'm not personally a big fan of these myself here, but just to show or quantify, like look at the highlighted number here. So when we look at chi-square min versus the computed values for area ratio, mass dimension, and number concentration, for all of the mass dimension relationships and all but 2 of the reflectivity weighted regimes here, we ended up with natural variability just dominating, the total uncertainty. In other words, the size of the surface that you saw in the previous these sets of plots here. So natural variability, we noted, just dominated the measurement uncertainty. So of course that comes with the implication of, well, if natural variability is so big, should we continue to care about, measurement uncertainties? And I argue, well, we should absolutely, continue caring about all these things, because first off, there's only 9 flights examined here. And secondly, we really need to take a look. We need to look at more environmental conditions here, but this posed a very interesting question here, like with the natural variability, like result that we saw here, like, is there a way to tease out cases where that there's gravity waves present, or that there's turbulence present in the cloud? You eliminate that, or you deconvolve that from the base atmosphere that you're flying your plane through, and how do you get that natural uncertainty out of there? So this is where we transition the talk here from MC3 measurements to impacts, because the advantage that we had with impacts here, and this is still an ongoing field campaign here, is that there's a secondary aircraft here that's taking curtains of both X-band and W-band radar reflectivity here. So there were 2 yeah, two great cases here where you can see like clear oscillatory behavior, in these relatively high altitude, like just cirrus. One of these is cirrus and the other is just stratiform that's just kind of trailing from one of the snowstorm cases here. But there's clear oscillations in the Doppler velocity radar data here where, over the course of a couple kilometers, you're going from -2 to 2.5 meters per second to +2.5 to 3. Very intense gravity wave activity here. But another thing that's important to note here too, especially on the plot on the right here for this February 5th case, there's a few hidden eddies in there, where there's, localized high altitude, convection going on. It's, interesting to think about because it's not necessarily like a supercell thunderstorm or, stratocumulus convection where you clearly see, the turbulence at the top and then that, but the manifestation here in the Doppler velocity is undeniable here. And the amount of eddies that you have here are, pretty important to look at here. So why we would care too about gravity waves and turbulence, like how they would produce natural variability in these, in our measurements here and how we ultimately derive, a surface of uncertainty for fall velocity is that they rapidly warm and cool, pockets of air, on several, hundreds of meters to several thousands of meters or kilometers. Well, I should say about, 10 to 100 kilometers or so with the gravity wave. But the rapid cooling especially, can lead to rapid increases in ice supersaturation, which is conducive for new ice formation. Localized eddies, of course, can rapidly cool the atmosphere as well. They'll rapidly cool, they'll grow ice particles very quickly, and then that produces precipitation, of course. So when you get these pockets of turbulence or possible gravity waves, you're going to inherently introduce that sort of uncertainty across the, cloud structure too, because if clouds were, if the whole cloud convex and then, it's just trailing downwind, you would expect it all to, gradually decay on a slow enough time frame to where you would expect some sort of homogeneity. That's not the case, of course, when you introduce this natural variability here. So again, actually a very similar slide here. Why we care about fall velocity again here. So the next science question we talk about here is, can differences in gravity waves, turbulent and static atmosphere conditions explain natural variability in that? So for the impacts data, it's, quite similar here. This is actually still a little bit ongoing, and I don't have any like super cool surfaces to show here, but, unlike the MC3 data, we have the 2DS and the HVPS to give us our full size distribution, and then, continue processing that. But using the XRAD and the cloud radar systems here, we're also able to get a secondary source by which we can confirm the existence of turbulent eddies and gravity waves. So, and then our third measurement here, where we did not have available for the MC3 campaign, but we have available for the impacts campaign, is the turbulent and air motion measurement system, or the TANS measurement. It uses vertical wind speed data to assess, well, we use it to assess the strength of turbulence. And then across, 10 minutes or so, we identified about, 6 for this talk, I think, but 18 in total, I think, that we are continuing to look at here, flight legs that use TAMS to proxy the presence of gravity waves. So let's take a closer look at 2 of these cases here. I have about, we'll say about 7 or 8 more slides to go here, so we'll be wrapping up here very shortly. But very first, let's look at gravity waves here. So again, as I showed on previous slides here, there's clear oscillatory behavior here. These are level flight legs, where the NASA ER2 aircraft is over top of the NASA P3 aircraft, and you get these, clear oscillations, which would indicate, there's, gravity wave activity that is almost certain to be there. But when you look closer at the reflectivity data, you are seeing, of course, these little eddies here. So you can call them eddies, but they're really, some sort of convective turret, like small scale turrets where you have rapid, a rapid updraft, it condenses, cools, precipitates ice particles at these 6 to 8 kilometer ranges here. So we confirm turbulence by looking at, the TAMS, and then we look at a wavelet analysis method here too that I'll show in the next couple of slides. And we also use, just again, the oscillations, from the Doppler velocity data as a secondary, more visual and qualitative source of confirmation here. So one of the things I guess that we want to do to make our our continued job easier at looking at gravity waves and turbulence is to more robustly quantify the, you know, the power, I guess, that's within these turbulent eddies and these gravity waves. So we employ the Torrance and Compo wavelet technique here. So this is a very handy, you know, like very well cited package here that's available to the public here. They originally developed this wavelet technique for ENSO analysis, you know, but, you know, it's been stated that you can use it for many, many applications like studying atmospheric gravity waves and study, you know, middle atmosphere, you know, gravity waves, you know, that are propagating into the, you know, ionosphere, you know, to the upper parts there, you know, synoptic scale wave patterns, Rossby wave analysis, Kelvin wave analysis. You know, you can even look at turbulence if you tune it to your data set and just look at it properly here. So for this, we take, you know, the basic package here, we implement it for the TAMS wind speed data to get a quantification of our turbulence and possible gravity waves here. So when we take the wind speed data, we, you know, convert that to, you know, we assume that to be a wave speed, you know, that's, you know, proportional, of course, to, you know, gravity, you know, and the periodicity of the waves, of course. You know, we ultimately want to see, you know, what are the scales of the turbulence and the gravity waves that we are looking at here. So what I'll draw everybody here too before wrapping up here is looking at, you know, look at the boxes on the radar curtains on the left here where we're looking at a turret. Okay, so, you know, there's, you know, clearing the Doppler velocity, clearing the reflectivity, the TAMS data that measured right through it, you know, very clearly some sort of eddy that's rapidly, you know, going from a -2 to -3 updraft to a +2 updraft very quickly. So that's about, you know, that's the magnitude of that shift is, you know, over 4 meters per second squared, which using a wavelet technique, you know, 4 squared, you know, if we're using wave speed would be over 16, and you get a very strong, significant turbulent eddy that's, you know, according to the output here, you know, it has a wavelength of about, you know, I would say that's centered probably on about 150 or so meters or so. So you have a 150 meter eddy, you know, very small scale, you know, it could even be a little bit smaller than that too. But, you know, that's more or less what it is. It gives you an idea of like what's the actual scale of the eddies here. And it gives us also a more clean way of distinguishing the turbulence, you know, turbulence that's evident in these clouds from the gravity waves that we also see here. So I want to point out one more thing too. So looking at the bottom right plots here, you know, we have our TAMS wind speed on the top here that we derive the data from. We look directly at the bottom here where there's, you know, these scales here, your wavelength. So anything that's less than about 200 to 300 meters, you can think of as a turbulent eddy, a small scale eddy, and anything more than 1,000 meters, you know, 10,000 meters, that'll be, you know, small to medium scale gravity wave here. And the reason you see kind of a bow shape line here that's meshed out a little bit, wavelet techniques, of course, one of the limitations of that is that, you know, given that it's clearly defined as a start and an end point where, you know, you don't know what happened before you turned on this measurement, you don't know what happened when turned on after. So anything near the edges is going to be ambiguous because, you know, the atmosphere could have been very static before that, or it could have been totally different. So the wavelet technique cannot compute waves properly due to these edge effects. And then, you know, at these larger scales where, you know, the aircraft truly can't see like a, you know, a 10 to 100 kilometer gravity wave because you only get 1, maybe 2 cycles at most. There's going to be some ambiguity there, but nonetheless, you know, it's still output. That's why we look at it anyways in context of the radar data, you know, because, you know, if there's 2 sources there, then we can safely say that that's likely a gravity wave. So that's what I want to point out, you know, in terms of addressing that uncertainty on top of what we're trying to look at in our cloud physics measurements, of course. So yeah, second thing here, just, you know, this is to train the eye more than anything, you know, it's to show that this is there. This is really important to look at. And this is why, like, you know, why we're trying to get at this natural variability problem. We really need to pay close attention to these small scale features in the measurement data and just really know what we're looking at here. Because the big thing that we ultimately see here in, you know, this particular case here is, you know, there's a gravity wave that's present here, but you have, you know, 1, 2, 3, maybe a 4th turret here. You know, you could argue if it is or not, but yeah, depending on where it's at, like, you know, the turret at the end here, it's, you know, looks like it's precipitating from about, you know, 7 or so kilometers or so. But then there's one, like, you know, a little bit before that, you know, maybe a couple minutes before, where you're piercing the top of the turret and it's precipitating downward. That's where you actually get the most turbulence. And that's how we have, pretty good idea that, we're at a relative like a cumulus cloud top here that's embedded within a gravity wave, because you see the most turbulence there, you see the biggest updrafts. And I think I didn't show this also on here, but I think we also saw like locally, a maximum in high ice water content, and only because you're at the top of a region of the cloud where the clouds are rapidly, producing ice and all that. So, same deal, I have one more case I'll show here. Again, just another set of where you see these, rogue eddies, producing, ice fall streaks in the cloud. And then we have a second one here where, relatively straight line, there's a little bit of a bank here, about admitted 20.55 to 20.56 or so. But beyond that, what we found interesting here was this was what the aircraft notes noted as a decaying stratiform structure here. And you can see that the turbulence mostly went away from the beginning of this, flight leg to the end of it or so. So you get all these noisy black, variations from the TAMS data, very clear in the turbulence that's ultimately retrieved by the wavelet method here. But by the time you get into this decaying region here, it's mostly a gravity wave at that point, because, the turbulence is mostly shut off. You're not producing much more ice. And then as a result of that, you get these much cleaner, the oscillations are on the order of, 1 meter per second to -1 to +1 to -1. All of this detrended, of course, because, you have to detrend the mean in order to use a wavelet method properly here. But that's interesting, and you definitely see, in the gravity wave part of the wavelet retrieval here, that there's definitely something on the order of about, based on the significant surface here, it's about, 7 to 10 kilometers or so here. So looking at the impacts data, we can definitely resolve turbulence at scales confidently at about 250 meters or so. We do the secondary verification with the radar curtains, and then the impacts 2020 data sets. We have, at least 18, with many, many more that we'll eventually look at here, because we also have, the 2022 data is being quality controlled now. Some of it's available, and then 2023 will be starting here in about another month or two or so. So we have a lot of data that we can look at here. So again, one of the limitations too, we'll say with the impacts, is that for 2020, we did not have like a truly independent ice water content measurement. I think we know that the WSPR is available, you could maybe get something from that, but Nevzarov was obviously my first go-to, because, already done that. It's easy to, cut and paste that, and just, tune the analysis to be able to do that. But it's all reflectivity weighting that we're working on for right now. So we think it's definitely likely that, once we get these gravity wave conditions fully teased out from the turbulent conditions, then, static, like let's say like an anvil cloud where, the cloud's mostly in a decay stage, we'll have a truly partitioned data set where, we know turbulence is present, we know gravity waves are present, we'll have cases where there's both present, and we'll have the static atmosphere. And then at that point, then we can start to say, well, if we're in static atmospheres, are we looking at, what regimes do the uncertainties from measurements really become that important relative to the atmosphere? That I think will be a good way to think about the fall velocity problem from airborne measurements. And especially when we get to a point, maybe, 10, 15 years from now, where we can actually measure that, maybe being optimistic here, but looking at that from like airborne measurements, once we have that available, then that's where, this framework I think becomes especially valuable here. But, it's definitely, worth doing right now. Continuing a lot of this analysis, we're working on the gravity wave and the turbulence aspect of the natural variability. Continue just looking at other methods, looking at other sources of uncertainty. Certainly, there's many cloud probe experts out there, that can chime in on their view of what sources of uncertainty are important and how we can use this framework to kind of look at that relative to what Mother Nature decides to throw in terms of their natural variability here. But we ultimately want to synergize these results from continental and tropical cases. We have this, mid-latitude baroclinic eddies, the mid-east coast snowstorms that we're looking at. We've already looked at the mid-latitude continental clouds, and highest water content. We were looking at that first, but we decided to look at impacts first just because, and, we'll continue doing that. So, and to conclude here, we do see, just kind of from the going back to the original framework from what we saw from the MC3, we did find that mass and reflectivity weighting is sensitive to environmental conditions. Reflectivity weighting certainly results in a wider spread relative to the measurement uncertainties. It's relative, but it does result in a wider spread. So there will always be more uncertainty regardless of what you're looking at. And the higher the altitude flight legs, we generally do see less overlap between, the equally plausible surfaces if you choose mass or reflectivity weighting. So I hope that, followed, as well as I could put it there. A lot of information here, and, but hopefully we all got the general idea of like how natural variability varies from measurement uncertainties in the context of aircraft, measurements that we use to derive these best estimate fall velocities, what we're doing to quantify the uncertainty, and how we're eventually going to, use that in looking at what what WARF, for example, might produce as an output. So with that, I thank everybody for their